Hello everyone, welcome back to the channel, and this is the episode 7 of our high level system design playlist. And in this video we will take a look at a very important topic, which is caching in distributed systems. Okay, in distributed systems. So this is a very important topic, and let's dive right into it. So this will be the flow of the episode. So first we will cover what, why, and how of caching. Okay, what basic we will cover the basics, what it is and how it is done, how it's implemented, why it's even needed. Next we will move to the types of cache. Okay, what are the various types of caching available. Then we will see what are the various caching strategies available. After that, we will take a look at the different cache invalidation strategies. Then at step 5, we will cover various cache eviction policies. And then finally, we'll end with the standard or a very critical production level problem, that is cache stampede problem. So let's start. So let's start with the section 1, and we'll start with the very basics of it, that what is caching. Okay, so caching is basically nothing but storing data that we need temporarily with us in a faster and a quicker storage. Okay, so that we can have a fast and quick access to that same data later. Okay, so this is the flow, as you can see. So let's say this is our server. Okay, and we get some requests. We are getting some requests for some data. So, and we are talking to a database, that is our data source. So what we do is we keep a part of the frequently accessed data here with us, so that whenever we get the request for the same data, we don't have to travel to the database again and again. Okay, so we keep it with us, and from here only, like, just using our data here only, we can just serve the request. So this will be our request, this will be our response. Okay, so basically this is the funda of caching. And so this is a very a sort of layman definition of it, but I think this will help you understand. And then slowly we'll build on this concept to understand how it is implemented in distributed systems and in high level system designs. Okay, so why is this important in distributed systems? Okay, because first thing is latency. Latency is a very big challenge in large scale systems, and caching the correct data can help you reduce the latency, and it can also help you reduce the load on your actual database, because your cache layer can act as a sort of screen on top of that database. Okay, it can just uh, save the very frequently accessed data, so that it all the requests do not end up going to the database layer. Okay, and in doing so, in reducing by reducing the frequent visits to your database layer, you can also save costs, because database access is quite costly. Okay, and all of this results in improvement of availability and also a better user experience. So this is a flow showing the same. Basically this is our user, and the user places a request to a server, and the server is talking to a DB. Okay, in a normal flow without caching, every flow will hit the DB, and let's say if three users simultaneously request for the same data, will end up executing three similar database queries to serve similar type of requests. The improvement on this is introduction of a caching layer in between. Correct? If we introduce a caching layer in between, what it can do is, for the first time, whenever a user comes and they want some data, we go to the database and we get the data and store it in the cache. From the next time, whenever other users come, what we can do is we can use the data stored in our cache, and we can serve it directly from there. Okay, so as we are introducing a new component in our system with our caching layer, we have some advantages and some disadvantages as well. So what are the trade-offs? Basically, by using caching, of course, we can improve the read performance of our system. Okay, which will improve the latency of our system also. Okay, and improving the latency will always end up help us in reducing costs, because we are reducing the round trips to database. Okay, the disadvantages of this is there is a risk of cache stillness, which we will discuss as we move on the video. Basically, the data in the become can become old and might not reflect the latest data that is inside our database. Okay, and handling all this is introduces complexity in our system, and distributed cache is a challenge that occurs due to its ring synchronization issues. We'll see all this step by step. Okay, so now we can check out our first box. So we are done with the basics of the caching, and now we'll see what are the types of caching. Okay, so to understand the types of cache, first we have to understand where can the caching happen. Basically, caching is what we are storing some data temporarily with us. So if we look at the data flow, okay, of a typical user, of a typical request in a client server architecture, the request flow starts from the user. Okay, so of course, first point of where the caching can be implemented is at the user's end, and that is called client cache. We save some important data at the users end itself, and that can help save some network latency and bandwidth. Okay, the second point is while we are at the network layer. So while at the network layer, we can use something called CDN or content delivery network, and we can use CDN maintained caching mechanism. So that is called CDN cache. Okay, so this that can help us in saving some static assets of our websites, and that can in turn help us in serving content faster. The third type of caching is implemented at the server layer, and that is called reverse proxy caching. So reverse proxy caching basically is that just before entering the request, just before hitting our server, we implement a component called a reverse proxy cache, and that stores some you know frequently accessed content of our server, like our static assets, HTML pages, CSS, JavaScript files, API responses as well. All this content it can store, and it can directly return this content from here without forwarding the request to the our server layer and then to the database layer. That's why it's called as reverse proxy. Correct. So this is the third type of proxy. Inside the server layer is where the fourth type of cache is implemented, and that is called app level cache. So what this means is all our application servers run some sort of code, be it Java, Python, Node.js, Go, anything. So all these applications have the access to in-memory caching, and they have various patterns of accessing this cache memory. So implementing this application level cache can also help us reduce our performance. Okay. Next, we move further, and we see a new component that we have is a distributed cache. So distributed cache is a very important topic, that that is handled in a distributed system. So what happens is in a distributed system, this box, right? This is a very important box because uh, there are multiple application servers involved, there are multiple database servers involved, and all these application servers need a common view of the caching data so that they can efficiently perform their operations. Distributed cache is this common layer of caching data. Okay, and this is implemented using several strategies which we will look further. So this is the fifth type of caching, that is the distributed caching. Okay, finally we have the sixth type of caching that is implemented at the database level, that is the DB level caching. So DB level caching mainly involves pinning of frequently used queries, or pinning of frequently used indices to make queries faster and stuff like that. So these are the various types of caches available. Now let's look at each of them. So first one is the client side. So client side cache is implemented at the browser or the mobile app level. Okay, and it basically caches images, CSS files, etc. Okay, and it is used for rarely changing data. Okay, so the points to remember for this is the expiration time for this type of cache is controlled by the app or the device in which we are hosting it. It can't be shared across multiple users or devices as it is in the local user or the device. Okay, as it is in the local device. So this is about the client side cache. Now comes the CDN or CDN cache or the content delivery network caching. So CDN is basically a geographically distributed network of servers that can be used to serve your content fast. Okay, so let me explain this with an example. Let's say we have a website called abc.io, and we start our website, we start our business from India. When we start our business from India and we our website goes live, people from London and people from San Francisco start accessing our website. Okay, as they are geographically very far away from us, right? So they are very far away from us, that's why they start experiencing latency while accessing our website. Now there is some complaints that our website is very slow, and then we start thinking that okay, how should we start solving this problem? To solve this problem, what we do is we go and collaborate with a CDN solution provider. Okay, for example, Akamai, AWS, GCP, and others. So what CDN solution providers do is they have their servers installed at different places across the world, and these servers are strategically placed so that they have some or the other servers for each and every location that you want to serve. So now as we are now onboarded with the CDN solution provider, what they do is they take the static assets of our website and they sort of create a copy of the same on all of their server network installed across the world. And these server networks are called global edge servers. Okay, edge servers basically. So what this does is whenever our London customer tries to access abc.io, first, their request will hit one of the CDN servers on that is nearer to them. Okay, let's say it hits the Scotland server. Okay, or it hits the France server. And what it does is because the actual geographical distance is very less, it reduces the latency a lot, and they experience a very fast loading of the website. Similarly, it happens for our San Francisco customers as well. So this is how CDN can help us, and CDN solution providers also provide the ability to cache our frequently used data. Basically, what files we can store there is we can store static files, that is HTML, CSS, JavaScript, okay, or whatever the images we have, okay, and advanced CSS can also allow you to store API responses. Let's say some few API calls are being executed multiple times. So these CDN servers can also help you to store API responses so that you can serve them directly from the CDN network. So how does the user flow work? So basically, let's say the user makes a request. Okay, the request first, instead of going directly to the origin server, the request first goes to the edge server here. So once the request goes to the edge server, if the edge server has the latest data, then it will just treat it as a cache hit. The cache works and it will return the response. If not, then the edge server will query the original server and it will treat it as a cache miss, and it will fetch the latest data, it will store it with itself, and it will return the response back to the user. Okay, so the advantages of this approach is that the latency is reduced a lot, and when the latency is reduced, the load on the DBs, the load on our original server is also reduced. This in turn reduces the cost, and also CDNs provide DDoS prevention, denial of service attacks. The cons is we are introducing a new component in the system, that is the CDN edge, and there is also cost involved with onboarding to the CDN solution service provider. And the second one is cache invalidation issues. Okay, the one we saw here, like if the data is not there on the CDN cache, then the CDN has to again communicate with the origin server and reload the data. Okay, so for solving this cache invalidation issue, CDNs generally implement URL versioning solution so that they can refresh their cache at the right time and they can provide the latest assets. So how it works is, let's say we have our style.css file hosted inside our server. Okay, and let's say as part of a bug fix, we are updating our style.css file. So what we will do is we will append a version to the end of our style.css file, and we will inform the CDN that hey, our CSS file has updated, so please update yourself. So the CDN will update its style.css file, and it will see that okay, the latest version number is 2. So for every request it will just pick up this version number, the file, pointing to this version number, and it will serve to the customers. In this way it can solve the versioning issues. The third type of cache is reverse proxy cache. Okay, so the reverse proxy cache sits in front of our, just in front of our application server as a proxy server. So why is it reverse proxy? Because it works both ways. So what it does is, let's say a request comes from the user. Okay, and once the request comes from the user, if the proxy has that data in it, it will just return it from here. If it does not have that data, okay, then it queries the database, okay, and it stores that data in it and returns to the user. So what it does is, what it becomes sort of a wall in front of the application server. Okay, it sits in front of the application server and intercepts incoming requests. Now the caches responses from the backend to reduce the load and the latency. Correct. So what can it store? It can store HTML pages, it can store API responses, and also application template files. Okay, basically let's say you have some UI templates to generate various types of UI forms, elements and stuff. It can store all that. Now what is the benefit of using it? Of course it will lower the latency and cost, and it will provide a better user experience. But this can't be used for dynamic content. Okay, and it should not be used in systems where high consistency is a must. Correct. Why? Because let's say the reverse proxy does not have a mechanism to frequently update uh, data from their database. So critical data which needs immediate updates should not use reverse proxy setup. Now what is the differences from of reverse proxy cache and the CDN cache? So let's look at that. So in terms of location, the CDN is globally distributed across edge nodes, right? But the reverse proxy is deployed closer to the backend, ideally on the same data center. And when it comes to what types of files these can store, so the CDN can store static assets like HTML, CSS, JavaScript, and the reverse proxy can store ideally any content. Mainly, it stores static content and also dynamic API responses, template files, and other things. In terms of control, like what kind of control we can exhibit on this, CDNs are generally controlled by the third party with whom you are getting onboarded, right? And the reverse proxy, we are the owner, we are, because we are the ones implementing it. In terms of configuration abilities, CDNs provided limited abilities if you are using the free version, but if you are a paid customer, I think you have good control there as well. And reverse proxy, of course, as you are the one implementing it from scratch, you have full control using headers. Okay. So when should we use reverse proxy? Basically, when we need full control over what is being saved and what not. Okay. And if the data is changing very infrequently, then it becomes a very good use case. Okay. Because it can reduce the load from the backend and it can serve the same content directly. Okay. And it is used for caching pre-rendered pages. So so let's say your website has have some static pages, some templates, some layouts. It is used for caching all that. Okay. Ideally, I've seen a hybrid approach being used where we go for a CDN edge network. Okay. In case the CDN edge network does not have the latest data, the request comes to the reverse proxy first. If the reverse proxy can serve the data from here, it's well and good, they return from here itself. If not, the request is forwarded to the backend server, and that for further fetches the data from the DB and updates all this caches here, and the data finally reaches the user. Okay, so this was the reverse proxy cache. Now we'll move to the fourth type of cache, that is the app level in memory cache. So this is a very smart and sort of technical implementation. So it is basically a local cache, and it is the cache that every process running inside our operating system or in a distributed system, we have various app instances, right? So every app instance will run its own process, and every process will have its own cache memory access. Correct. So let's say you are running a Java based backend or Node.js, Python, whatever. So every process will have its own in-memory cache. Okay, for example, JVM in-memory cache. So this cache lives inside the JVM or Node.js or any Python process, and it stores frequently accessed data that is needed by the process to run. And it is extremely fast with less than 1 millisecond of access times. So generally in Java, caffeine library is used a lot for accessing and creating an in-memory cache and using it. And similarly, concurrent hash map and Guava cache is also used a lot. Go has in-process map implementation via the group cache. Okay, so the hierarchy of how the data is accessed in the system is: first, the process checks in the local cache, that is let's say that is supported by JVM. If it is not there, we check in the distributed cache, let's say that is supported by Redis. If it is not here also, uh, we check the database. Okay, and this is after the request has reached the application server. It has crossed the CDN, it has crossed the reverse proxy, and it is inside the application server. Then this request pattern is hierarchy is followed. And point to note here is the latency increases as we go down. So JVM is the fastest, Redis is slower, and the DB call is the slowest. Okay, so what is stored here basically? So inside the in-memory cache, we generally store values like the feature flags, environment config files, metadata, session data, okay, recently accessed objects that is stored in the heap memory. Okay, so recently accessed objects, and mainly all the data that is being highly read by the system process and not written. Okay, and what we should not do is we should not put files with big like huge size inside this in-memory cache, because that will fill up the heap memory, and it will throw heap overflow errors in Java, and similarly in other languages as well. So example is Netflix also uses this cache warm-up technique to load all its application server with config files at startup, and it is quite popular uh, for storing data like the user type, product flags, basically infrequently changing data, okay, are kept in the memory. So this was about the uh, in-memory cache. So the next type of cache that we have is distributed cache, and this is very very important in a distributed system. The major implementers of this distributed cache is Redis and Memcached. Okay, so what is this basically? So this is basically a caching layer that stores key value pair inside fast access memory, that is RAM. Okay, it lives it outside the application server, and it is shared across multiple instances, and that's what makes it very very useful. Okay, it is optimized for low latency and high throughput. So what is this? Low latency means we can access quickly. High throughput means a large number of volume of requests can be done. Okay, now why did we need it? Why did we need a new caching layer? So the other types of cache that we saw, that were at separate points of the data flow journey, right? And inside a distributed system, we have multiple application servers which need a common view of the caching data, so that they can make use of the caching data to reduce latency even further, so that they can handle a high amount of read traffics. Okay, and also they have to lower the db pressure a lot, and hence a separate caching layer is formed, which can give a common view of the caching data to the multiple application server layers. Okay, so a typical flow looks like this, where a request flows in from the user, and it comes to our app server. Here app server has local cache implemented, and it also has access to what we call our distributed caching system or layer. So what this has is, it's a layer in between the database and the application server, and it has all the frequently accessed data that can help the app server serve this request even faster without reaching the database layer. Okay, so this is basically the distributed caching layer. And what do we store here is mainly data that is shared across multiple app instances, that is, let's say, frequently read objects, already pre-computed values. This is the main use case, so that other app instances do not have to do the same computation again, and we can store shared data and session and token data in this as well. So there is a concept of TTL and expiry in the distributed caching layer. So basically TTL, or time to live, is set based on every key, and it specifies that after how much amount of time every caching key, cache record or key will become stale, so that it can ensure that the stale data does not live forever inside the system. Okay, and inside the distributed caching layer we have to incorporate invalidation strategy as well. Okay, so that we can solve the problem of stale data. So there are various invalidation strategies that we will see in the upcoming in this video. So there are a few pitfalls here. Basically we have to deal with stale data. Okay, and we have to deal with the cache stampede, or the thundering herd problem. Okay, there can be scenarios where the redis can be down, or basically our distributed caching layer can be down, and we have to have good fallback mechanisms for that. And there can be memory bloating in the distributed caching layer. Basically we end up storing files that are of large size, and that can hurt us bad as well. So this is a comparison table, basically comparing the various types of cache, and this is for your reference. You can just go through it, and it can give you a concise view of which caches to implement at what point in your design journey. Now let us move on to the section 3 of our video, that is caching strategies. Okay, so caching strategies involve keeping cache data fresh and consistent. Okay, so there are two types of caching strategies. Okay, first is one is the read related strategy, and one other is the write related strategies. Okay, so as we already said that why we need caching strategies, because we have to keep our cache data always fresh and consistent. These two are the main points. So let's see what are the various strategies present under the read strategy and write strategy. So under strategy, we primarily have three cache access patterns. So one is read through, one is cache aside, and the third is refresh ahead. Under write strategy, we have three patterns, that is write through, write around, and write behind. Let us look at what each of these are. So let's first see what is read through cache. Okay, so basically the one liner for read through cache is cache only on the first read. So this is our user, and the user executes a read request to our app server. Okay, our app server, what it does is it checks the cache first. It checks the cache. If the cache has the latest data, it returns it here, and if it does not have the latest data, which on the first read ideally it won't have the latest data, so it goes to the database, it queries the DB, and then it comes back and updates the cache with the latest data, and the subsequent reads are then served from the cache. Okay, so basically it first checks the cache if the data is there or not. If it is not there, it queries the database and fetches the data and updates the cache, and then it returns the required data. So the advantages of this approach is it is very intuitive, and hence it is very commonly used. Okay, and it ensures that actually the actual popular keys, or hotkeys in your system, are always stored in the cache. Okay, the disadvantage, as you might be noticing, is the first access is bit slow. Okay, and as the first access is slow, it can lead to cache stampede problem, which we'll see uh, in the upcoming sections. So this was about the read through cache. Next we have the write through cache. Okay, so write through cache says that update the cache whenever the DB is written. Okay, or whenever the DB is updated. So what the typical flow looks like here is, let's say this is our user, and the user executes a write request on our cache. Let's say the user wants to write the data 1 comma abc. Okay, now what happens is the request flows into our app server, correct? The app server, what it does is, as it is a write request, according to the write through policy, it executes the write query both at the database and at the cache. Okay, it writes or updates the cache whenever the DB is written or updated. Okay, so the best advantage of this is the cache always stays in sync, correct? The cache always stays fresh, and there are no stale reads in this pattern. The cons with this approach is, as we are introducing two write operations for every write, the write latency increases a little. Okay, and hence, as the write latency is increasing, it is not very suitable for data that is being updated frequently, or frequently updated data. Clear? Now let's move on to the third policy, that is the write behind, or also called as write back policy. Okay, so what it says is, can I cache the data now and update the DB later? Okay, so the typical flow would look like this. So let's say a user makes a write request, and the write request is received by our app server. Okay, initially what it does is, it stores the data in the cache, it writes the data in the cache. Okay, and at the background it will just execute a asynchronous job that will update the database and bring it in sync. In the background it will just update the database, and it will bring the cache and the DB in sync, like this. Okay, so in this approach, the advantage is that the writes become very fast, because we are only writing to the cache immediately, and cache writes are quite fast. And we are executing or initiating a background job that will update the database eventually. Okay, so this is about write back policy. So as the writes are very fast, this policy is great when the use case involve analytics, or non-critical writes. Why non-critical writes? Because of this con, that the background job might fail, right? This job that we are executing at the background, it might be a possible that this job fails, and if this job fails, then the database does not get the latest writes from the cache. Okay, and this becomes the con of this approach. Let's say somehow the cache goes down, or our background job fails, then the consistency of the system is compromised. Now the fourth type of caching policy or caching strategy is cache aside. Okay, this is also called lazy load or lazy caching. So what this says is, or rather what this asks you is, should my app fully control the cache control logic? Okay, if this question's answer is yes, then you are good to implement cache aside policy. Let's see how it works. So let's say this is the user, and they have created a read request to your app server. So in this policy, what is done is, at first step, the database is queried. The read request is forwarded to the database. Okay, and the response is written to the cache immediately. Okay, so basically the cache is set aside. And why is it lazy loading? Because we are lazily populating or updating our cache data, correct? On the first request, we are first querying the DB directly, we are getting the response, and that response we are storing in our cache, correct? So basically the entire cache control logic is controlled and managed by our application, and the rights are also managed by our application. So the total control is in our hand. Okay, so this total control is what becomes the advantage of this approach. And this approach is very commonly used in microservices architecture, because we have full control of what we are reading and what we are writing to and from the cache. Okay, and because we have total control, and because we implement it from scratch, it is little harder to maintain it. And the stale data, if the read write logic is messed up, we can it can result in stale data. Okay, now let's look at the fifth cache policy, that is refresh ahead. So as the name suggests, this caching policy asks that, can I refresh the data before the expiry of any data inside the cache. Okay, let's look at an example. Let's say this is our user and they execute a read request on our application. Okay, so what our app server does is, our app server, in the background it runs periodic jobs, that will just straightforward, they will update all the entries in the cache which are about to expire. Okay, let's let's assume that our cache has an entry called with the key 1 and the value abc, and the ttl is, let's say, 10 seconds. That means it will expire in the next 10 seconds. So one job will run that will automatically update and automatically query our database and update our cache with the latest value that we have stored against this key in the database, and it will store it with its updated timestamp. So it basically refreshes the cache ahead of its expiry time, so that the cache always has the refreshed and latest data. Clear? Now we move on to the final caching policy, that is write around. Okay, so in write around policy, what we do is, let's say this is our user. Our user executes a write request. Okay, at the first step itself, so this is our app server. At the first step itself, our app server will directly write the data to the db at the first step itself. So when the next read request for the same key comes, the query is again sent to the database server, and the response is returned here. As you can see, the response is returned, and the same response is stored in our cache here. So we have the data 1 comma abc stored in the cache. Okay, after this what happens is, all the subsequent read requests can read it directly from the cache. So this is write around policy. Basically, first we are writing to the database, then on the first read requests, we are reading from the database, we are getting the latest value, we are updating our cache, and in result, all the next and subsequent read requests store the data directly from the cache, and the latency is reduced. Okay, so this was it about the various caching strategies. Now let's move on to the section 4 of the video, that is cache invalidation and consistency. So cache invalidation is a very important topic, and let us understand what it is. So cache invalidation basically involves removing or updating stale data from cache. Please mark the word stale. Okay, so whatever data becomes unusable in our cache, we have to have a mechanism by which we can remove or update that stale data. Okay, so that is what is cache invalidation strategy, and it is different from cache eviction policy. Okay, so cache invalidation ensures that our cache has the correct data always. Okay, and this is especially very important in write heavy systems, because continuously the data is being updated and the cache has to keep up with the database, and it always have to have the real time updates. Okay, so why is this problem considered hard? So in distributed systems, the caches are also distributed, right? They are spread across multiple regions, multiple data centers, and multiple availability zones in a cloud-based architecture. Okay, so writes. So in such a system, writes might go to databases directly, and cache might become unaware over time. So this is the problem that we have to solve. That we have to keep the cache and the database in sync always. Okay, also crashes and race conditions contribute to this problem, and they result in partial writes, which make cache invalidation a hard problem to solve. Now we'll take a look at what are the various cache invalidation techniques that are available for us to solve the problem of cache invalidation. So the first technique here is invalidate on write. Okay, what we are saying is, whenever we have a write request in our system, okay, immediately we will write the data to our database for sure, and at the same time we will also update our cache with the latest data, or we will make it invalidate. Correct, we will delete that data from the cache whenever a new write request fails. So in this way Okay, in this way we say that okay, our cache can never have basically the wrong data or the old data. So automatically this results in automatic up to date cache, and the behavior also becomes quite predictable. Okay, and the disadvantage of this approach is in case somehow the cache deletion fails, okay, this cache deletion action fails, then it results in a stale data. Okay, and hence it requires strong decision discipline in our code, basically implementation of common utils or common framework that can handle that whenever there is an update on the database, automatically query the related cache and delete it. Okay, the next cache invalidation technique is TTL based technique. So what is TTL? It is basically time to live. Okay, time to live means in how much time will this current cache record expire and become stale or unusable. Okay, so what this approach says is fix the expiry time when inserting to a cache. Okay, if we fix the expiry time when inserting to a cache, if we fix this expiry time, what it will do is it will create an automated approach where whenever any cache reaches its expiry time, or its TTL time, it is automatically removed or deleted or invalidated from the cache. So this is a very simple and automatic approach that we have. Okay, but the point to note when using TTL based invalidation is we should not use it for frequently updating content. Okay, let's say we use this same technique for a data where say we write a key 1 and value ABC and set the TTL to 10 seconds. Okay, so every 10 seconds what will happen is this cache has and this record has to be deleted or invalidated from the cache, and that is not a very efficient thing to do. Okay, so now let's move on to the third technique of cache invalidation, that is write through or event driven invalidation. This group is also known as push based invalidation. Okay, so let us look at the write through invalidation. What this saves that whenever we have a write request on our app server, okay, we execute simultaneous updates to both the cache and the database in the same transaction. Okay, we execute simultaneous updates to both the cache in the same transaction, and this can help us coincide the status or the state of both the cache and the database. Clear? Now let's move on to event driven system. So event driven system involves uh, the flow where we have a write request on our app server. Okay, what happens is the app server sends the write request directly to our DB. So in our DB we get the latest data, correct? Whenever the DB has the latest data updated, the DB has a trigger written on it. So what this trigger does is it puts an event on a Kafka queue. Okay, and on this Kafka queue, what we have is we have a consumer that is listening to it. We have a consumer that is listening on this Kafka queue. Once this consumer gets a new message, okay, what it basically does is it goes and it invalidates the cache. It goes and it invalidates the cache. So you're clear with the flow, right? The write request comes, the app server receives it, it writes the updates in the database. Once the database rows are updated, the trigger is fired. The trigger puts an event on the Kafka queue. The consumer who is subscribed to the Kafka queue received the message, and based on the message they get to know that okay, we have to invalidate so and so key. So it invalidates, let's say, the write request for 1 comma ABC. So at this message it will say that okay, has been updated with this ABC key. So now in the cache the key with the entry with key 1 is deleted or invalidated. So this is how event driven cache works. So this approach is very commonly used in microservices architecture, and it is scalable as well. Okay, because we are introducing independent components that can scale independently. Okay, and it prevents missing invalidation due to logic bugs that can occur in the above approaches that we discussed. The disadvantage of using this approach is it introduces a new infra complexity because we are introducing a new message queue, okay, and we are also introducing a new consumer component, and all this needs event handling, which should be idempotent in nature. Okay, so in this section, the golden rule that we found out is that always invalidate or update the cache after you are updating your database. Okay, always, this we have to do always. So database updates should always result in cache invalidation, and for that purpose we can choose any of the five approaches that we discussed above. Okay, now let's move on to the section 5, that is cache eviction policies. So what this section is, so now we just discussed the cache invalidation policies, which work when the existing data inside a cache become invalid or stale. But what happens when the cache is full? Okay, how do we remove the data? How do we choose which data to remove? This is what is governed by cache eviction policies. Okay, this is how cache eviction policy and cache invalidation policy is different. So why this is even needed? Why can't we have infinite amount of memory so that the cache does not go full ever? So cache memory is limited, and infinite cache memory is not a feasible thing to have in our system because cache memory is very costly. Okay, hence we have to have a strategy to decide what to remove. Okay, for example, let us consider we have a fridge. So this is our fridge. Inside our fridge we have few items. Okay, this is our item 1, item 2, item 3, and item 4. So item 1's expiry date is 2. Okay, this is the expiry date. Items 2's expiry date is 4. Item 3 is already expired, and item 4's expiry date is 2. Let's assume that a new item has come to us that we have to store in our fridge, that is item 5. Okay, and the expiry date of item 5 is 2. Now the fridge does not have any new space, any more space to save. So what we have to do, we have to remove an existing item from the fridge. So of course, which one we will choose? We will choose the one which has already expired. Okay, so you see, right, that how do we make space for new and updated and refreshed data or refreshed item? We remove the existing stale item which can't be used anymore. So this is what is cache eviction policy. How do we decide on which, based on which parameter and which property, that which data to remove from the cache, so that we can store the latest data in our cache. Okay, so let us look at the various policies that we have in place for solving this problem. So the first one is LRU, or least recently used. So as the name suggests, we maintain a usage history of our cache records, and when the cache is full, we remove the oldest used record. Okay, so this is implemented using doubly linked list and hash map, and that is a very standard implementation, and it is also a real world access pattern that is used in a lot of libraries, for example in Redis as well. Okay, the disadvantage of using this is many a times, as you are maintaining a usage history, right? So in the usage history, let's say your table or database, the last few items are not very frequently used items, but still you end up storing these items. Okay, because of the nature of the algorithm. Clear? So this is the LRU policy. Next we have LFU policy, or the least frequently used. Okay, here for cache removal, what we do is we maintain a usage counter for every cache record, and whenever the cache becomes full, we evict the least accessed item. Okay, so the major problem with this approach is maintaining a global counter, to check how many times the cache records were used is quite costly. Computationally it is costly, and basically we have to have some sort of min heap implementation, and then sorting that complete list. Let's say you have millions and millions of hits on your cache, and then sorting that data, and then removing the least frequently used is computationally a lot uh, like costly task to do. The next cache eviction policy is random policy. So this is very simple. Basically, we just pick and evict a cache, and this is totally randomized. Is good for caching that kind of data which is not very important, and where we can bear some loss, or sudden removal of caching data, or let's say hotkeys are also might also get evicted because it is totally randomized. So this is random pick and evict methodology. Next we have FIFO. FIFO is also a very simple approach where it is a first in first out. A simple task queue is maintained, and the uh, records that go into the queue first are evicted first. That is as simple as that. Next we have a TTL based approach. Okay, so basically we are already setting TTLs when adding entries to the cache, and the entries are being auto deleted on expiry. Okay, so based on TTL also, the eviction policy works. Okay, so when we are using TTL, what happens is we guarantee freshness of our cache, because we are automatically removing the stale entries from our cache. Okay, and there is no manual intervention needed. What is the con of this approach? It is not access based. Okay, it is just plain time based, and it is not an access based mechanism, and you can't control that which cache is being removed based on the access. Correct. So next we have the manual control. So the manual control in the cache eviction policy, it can provide you a precise control of exactly which key to remove. Let's say you are running a command like del key key a, okay, inside a cache. What it will do, it will just straight away it will go and delete the key and the value corresponding to this key. Okay, so this offers precise control over what you want to remove, and it is generally used in business critical updates. Let's say we have recognized the key which should not be there inside the cache, but somehow it has landed up, so we just simply go and delete by the key. Okay, so most modern systems will use a combination strategy of all this. Basically, for freshness they will surely go for a very simple approach of TTL based eviction policy. For memory control they will use a combination of LRU and LFU, and for business critical updates we will use manual cache eviction policy. So this was it about the cache eviction policies. Now let's move on to section 6 of our video, that is the cache stampede or the thundering herd problem. Okay, so this is a very critical issue that is observed in production systems. So let us discuss what this issue is. So this is our cache. Okay, let's say this is our cache, and let's say we have a read request for the key 1. Okay, for the key 1. Okay, and for the key 1 we are expecting a value of abc. Okay, so when the read request for the key 1 came, the cache did not have this key 1 stored in itself. Okay, so it has to query the database, right? It has to query the database for getting this key and updating itself. But what happens is we get 1 million simultaneous requests with this key 1 at the same time, and as the cache does not have this data, or it might be expired as well, what happens is all these requests try to go to the database and fetch the latest value, and that's where the thundering herd problem is created. So you see here a herd of request is created at the cache, and there is a cache stampede. Okay, all of these requests are trying to go to the database and fetch the latest data, and due to which the system crashes. So multiple requests for a hot key, when they come in while the key has expired and the DB refresh has not yet happened, this situation is what is called cache stampede or thundering herd problem. Now, for preventing the cache stampede or thundering herd problem, what are the solutions that we can adopt? So the first solution that we can take is applying mutex or locking. Okay, so this is a very intuitive approach, where what we do is after we encounter the first miss, we say that one request can update the DB. can take the updates from the DB, and others have to wait in the queue. Okay, so how the flow works is the user executes the read request for the key 1. The cache checks itself and finds that it does not have the key. As it does not have the key, it acquires a read lock over the record inside the database. Okay, that it is reading that record from the database and no one else can read it. Okay, once it has read the record from the database, it updates itself. So it sets the cache and it updates itself. Once it updates itself, okay, it releases the lock. Okay, and while all this is happening, all the subsequent requests that were coming, they have to be at a waiting status. Once the lock is released here, they can again acquire this lock. They can again acquire this lock here, and they can start executing. But they don't need to acquire because the cache is now already warmed up with the latest data for the key 1, and it already has the latest data. So now all the subsequent requests can be served from the cache itself. So this is done using mutex or locking. Okay, so the advantage of this is it will always guarantee 1 dB hit, because for the first request itself the database will be hit and all the subsequent requests will be served from the cache itself, and hence it provides the stampede. It prevents the stampede problem. Okay, what are the disadvantages of using this? We are introducing latency in the system because the other requests have to wait here, and the lock management is quite tricky. Okay, so basically let's say we have to write mutex statements like this that set nx lock key. So we lock, we use the lock keyword on which key want to lock. Then we do our operation, basically read the value from the db, and then we delete whatever lock we had set on that key. So this is how we write the mutex for setting acquiring the lock and then reading from the database. Okay, now let's move to approach 2 of solving this same problem. In approach 2, we use a technique called request coalescing. Okay, so in request coalescing, what happens is we combine multiple concurrent and identical database requests into a single DB request. Okay, and this is done at a programming language level. For example, Golang uses single flight, which does this. So this is a very smart and efficient way of combining multiple and same read requests into one request, so that the thundering herd problem is resolved. And it is very popular and implemented at large scale CDNs. Okay, the disadvantage of this approach is we need to set up this orchestration at the app layer, and that requires critical code changes. Okay, let's take a look at the third approach for solving this problem, that is stale while invalidate. So in this approach, what we do is, if we get a read request, let's say we get a read request with key 1 and our cache already has the data of key 1 and value abc, but it is stale data, we just return the stale data temporarily. We return the stale data temporarily for the first few requests, and we start an asynchronous update job. Okay, this asynchronous update job will update the required data from the database in some time, and what will happen is after the next few requests, the read requests which come for r1, all these r1 requests, all these are served with the latest data, with the latest data. So basically for the initial request we are just serving the stale data for now, and immediately we are triggering or starting an update job which updates the data as soon as possible, and then it starts serving the latest data. So the advantages of using this is we are reducing the wait here, there is no wait, and of course this also reduces the db load. Okay, and the disadvantage is the first few requests are getting the stale data. Okay, so this was approach 3. Then we move on to approach 4 for solving this problem. That is also called jitter. So what we do is, it's a clever sort of trick that we apply while setting the TTL. Okay, while setting the TTL, we add a random value of, let's say, 10 to 15 seconds or 20 seconds 2 hour TTL time so that similar keys do not expire together. Okay, we prevent this situation where similar keys might be expiring together and causing the thundering herd problem. Okay, but still, even if you introduce some amount of randomization, you cannot guarantee that the stampede herd problem is completely prevented. So that is the case here. The final approach that we have for solving this problem is cache warm up. Okay, so cache warm up is a technique that has been used at top engineering teams very frequently, and basically this involves refreshing the keys in our cache with a background job, typically before their expiry. Okay, so what this does is your cache will never expire, and if your cache never expires and always has the good data or stale or not stale data, no DB access is triggered. If no DB access is triggered, you automatically prevent the thundering herd problem. Okay, and the main thing that we're depending on here is on the background job, correct? So the background job must be very robust, and then it can only help to prevent the thundering herd problem. Okay, so with this we come to the end of our video today, and I hope that it was very helpful for you, and you got to learn few things about caching in distributed systems. So let us mark all these as complete. So we saw what, why, and how of caches. We saw that okay, what all types of caches are there. We saw all the caching strategies that were available to us. Okay, then also we saw how we invalidate caches. Okay, what are the strategies for invalidation. Then we saw that what is cache eviction and how it is different from cache invalidation, correct? And finally, we solved a very important problem. We saw the approaches to solve the cache stampede problem or the thundering herd problem.
So this was it about this video. I hope that this video helped you a lot in understanding caching in distributed system, and I hope that I could make good use of your time. And thanks again for watching it, and I'll see you in the next video.